Okay, good afternoon. My name is Eric Mas. I'm from the International Research Institute of Disaster Science, IDRC, in Tohoku University. What I'm going to share with you today is it's called the DIM2C project. It's a Japan-Israel collaboration on research for urban resilience simulation. This is a JST-funded project from the Japan side and a MOST project from the Israel side. My PI in the other side, in the Israel side, is Daniel Felsenstein. He is a professor in the Hebrew University of Jerusalem. So what this is our team from both sides in Japan and also in Israel. Our project is about about evaluating, planning, and mitigating possible impacts of large-scale disasters using it's called ICT, but it's generally simulation and web-based approach. So what is our approach? We want to integrate hazard and damage assessment models, also agent-based simulation, with GIS-based socioeconomic profiling to produce a web mapping product. This is going to be a scenario-based tool for disaster impact analysis. So the idea here is to generate multiple disaster scenarios as a testing bed for a discussion between disaster responders or stakeholders as a training tool. So the idea here is to develop a platform for interdisciplinary discussion where you can integrate what is the engineering, what is also the socioeconomic and the geographic and the planning of the urban resilience. The whole framework of the project is it has several stages. The first stage is having the census data, the aggregate data, making a profiling of individuals from the city, going from the census to the profiling of each person in a city, like how much is their income, how many families, what is their age, where does they live, etc. This is a synthetic, somehow quasi-real data because it comes from the census, but it goes to the very individual scale. And the second step is with this information, we generate the damage scenarios even from earthquake or tsunami. So we have these damage assessment models that is generally a top-down approach. I will show you later about that. And then from the bottom-up approach, we use the agent-based simulation, making the agents, the individuals, with these profilings to move along and to cooperate and to look for their restoration and relief after the earthquake. And then with that, we find a new equilibrium in the urban, in the city. This is called, in the whole process, is we will want to define as the urban resilience kind of index, how much time the city takes to restore their equilibrium. So the idea of the DIM2C model will be having the urban population in a pre-disaster situation in the upper part. You have the spatial database. With this database, you can, and the impact of a disaster, let's say a hazard scenario like a strong ground motion or tsunami inundation coming from simulation. You can generate earthquake evacuation or tsunami evacuation. And using the fragility curves for damage estimation, we generate scenarios of damages. With this scenario of damage, we know how much human losses are in casualties, estimated casualties. But also not only casualties, we go on also to see what happens with the survivors. I mean, they are already in the shelters, right? So how can we attend these necessities in the relief part of the shelters? And then we connect into the urban dynamics, which means that the damage state and the land use and the population dynamics after the disaster, it generates a new dynamics in the population. Let's say if someone has lost their work or their house, it's more compelling to migrate out of the city. If someone has their house, probably it goes back from the shelter to their house rapidly. So these kind of assumptions and tweaking these parameters, we can generate several scenarios, coming everything from the socioeconomic profiling. Everything is going to generate large information because it's individual disaggregated data. So we call it synthetic big data. And that information will generate a lot of discussion on what kind of policies we can do in a city to accelerate this restoration of the city or to make the population, to make the city more strong. We have two areas, one in Israel and one in Japan, which is Sendai and Haifa. As I told you, this is the first stage, which is coming from the census tract. We disaggregate this information of population into buildings, and then into households, and then even into individuals in each household. So the idea is that each individual will have, in their allocation, they will have income, age, employment, religion, ownership, whatever information we can have from the census tract data. So with that, we can generate the mapping of how this is distributed. And then with the information of the hazard, let's say some very traditional approaches of generating damage estimation. Let's say you use the peak ground velocity or the acceleration coming from an earthquake, and using the damage fragility curves, you can estimate each building's damage. So we can, if this is related to a household, we can know this household, how much impact they have in the individual scale. Another kind of approach, also traditional, is we use this, we test this in the Kumamoto earthquake, just to see how much this traditional approach of using seismic fragility curves for damage estimation gives good accuracy or not to the estimation of damage. And also we try to develop new methods using satellite images and remote sensing, and using the fragility curves to classify this building damage. The same approach is going to the tsunami, because we have also tsunami fragility curves. So tsunami fragility curves are also used based on the inundation depth estimated from either simulation or real cases. And then you can have also an estimation of the physical damage. From the Kumamoto earthquake, also we did a remote sense survey. We used satellite images to estimate how much building, when they collapse, they scatter the debris, and this debris can become disruption of networks, road networks. So what we did here is we observed each building and how much they collapsed. And then we created an empirical rule of how we can estimate, according to the building height, after the earthquake disaster, we can estimate how much this debris extend. And if this debris extend in the road, we can create a new disrupted network. This can be stochastic, or this can be aleatory using random parameters also. And the idea is to generate different kind of scenarios. So once you have the damage and you know what is the people at, you can generate also, using the agent-based model, you can generate the evacuation. How people move from their houses to the shelter or outside, whatever. So we generated agent-based modeling for evacuation. And also, once people is inside the shelter or you have victims around the area, how firefighters or ambulances or other kinds of responders will go to attend these victims, and how this can be optimized in a fast respond manner. So this is all agent-based modeling. And also other agent-based model approach is disaster relief support. As I told you, when we have different shelters, we need to attend the necessities of this shelter. At the beginning, we don't know what are the necessities of this shelter. So generally, we just send whatever, let's say, blankets or onigiris or whatever food you send first to gather the information on how much necessity there is in case the communication is disrupted. But there are other approaches and other strategies that can be evaluated according to the different situation of the disaster. So we are developing some kind of new model to evaluate these strategies. What if we have a disruption of the road network and we better generate intermediate gathering points so we can get faster and better optimize the resources we have. So, and then, as I told you before also, there's a socioeconomic side of this project, which is agents are related to the residential location, but also to their activities. They have everyday in a beginning of the simulation, they have an everyday activity. Let's say when there's no disaster, they have a job and they have a place to work. They can go to the market, whatever. And then when the earthquake strikes, it strikes not only the agent, but also the environment. So you have buildings and houses and factories and whatever is disrupted. So everything will have to be readjusted. And according to several rules that the agents follow, they can finally get to this multi-dimensional database. This is what is the housing value, the new housing values according to the impact, what are the urban morphologies, or the unemployment rate in the next years coming after the earthquake. So this part of the simulation is around like 2 to 3 years simulation, synthetic simulation. So what you can get here is land use change. According to these stock market differences and prices of building and migration of population, there is a change on the land use or expected possible change in the land use that we can estimate with these kind of models. And then all of this is integrated into a web-based platform that can be communicated to people and be the testing bed for training or for discussion among stakeholders. So just to let you know, we have a web page about this project, and I would like you, well, if you have time, to see it. I'm sorry it's not there. But if you look around DIM2C project, you will find our project and our progress in this topic. Okay, thank you very much.
I have a question.
Oh yeah, please.
Is it only for the stage of preparation of disaster, or is it also used in the disaster response phase?
Oh no, we want to do the whole stage of the impact, the relief, and the response, including relief.
For
and
planning, or
it's generally for discussion. It's generally to evaluate the urban resilience. Let's say how much time a city will take to get a new equilibrium, even if this equilibrium is better or worse than before. Okay. And then if you include a policy, let's say if you change something in the simulation, how much impact this has in the whole timing of equilibrium. And then you can have an index of this city has this resiliency value, let's say. Thank you.